Hello, my name is Olivier Moulinjeune from Extreme Engineering. I'm business development engineer in charge of material suppliers. Before to start, I want to thank DSM to give us the opportunity to present during this North American Advanced Material Forum. Today we are going to present how to address industry challenges with advanced material simulation. First, let me introduce Hexagon. As you know, Extreme Engineering has been acquired by MSC Software in September 2012, and in April 2017, MSC Software has been acquired by Hexagon. Hexagon field of activity are very diversified, from aerospace and defense to power and energy, and passing through automotive. The aim of Hexagon is to make the industry smarter by creating a strong link between real world and digital world to have dynamic data on which you can really act. Global research and strong financials are the DNA of the technology solution provider company. HMI is our Hexagon Manufacturing Intelligence division, focusing on smart factories. Purpose here is to have a deep understanding of industrial workflow. The link between the real and the virtual, known as digital twin, aims at mastering processes with software for design and engineering, manufacturing and metrology, but also with metrology hardware. Hexagon HMI provides best-in-class solution for smart factories. As you know, after a period of production offshoring, companies are now willing to reshore. This can be achieved with smarter production organization and simulation. MSC Software is providing virtual prototypes for manufacturing with Simufact and for structures, acoustics and fluids with Nastron, Mark, Actron and Cradle software. In the domain of autonomous driving, VTD, Virtual Test Drive, allows to simulate hours of driving in many conditions to accelerate validations. In the field of materials, Digimat from Extreme Engineering is pushing the limits of material modeling, addressing the challenges of new materials. Extreme Engineering is a team of passionate material and process experts. Our software platform, Digimat, aims at providing the best of integrated computational material engineering. Newcomer in our portfolio, Material Center is a preferred tool for material lifecycle management. Extreme is 15 years of double-digit growth and today more than 500 customers. The main domain of activity are automotive industry and material suppliers, but also aeronautics, electric and electronics, and R&D. We will continue growing thanks to this 10x strategy, and this is what we will talk about today. Virtual material development is the first topic we will cover, how to reduce costs with simulation. Then comes virtual material testing, where some huge savings can be found. Material lifecycle management is a growing subject as well as material exchange. How to bring the R&D work to the desktop of final users is what we address here. Compliance management is probably not the favorite topic of material scientists. Nevertheless, if it's not well managed, consequences may be significant on day-to-day business. Back to Extreme DNA, the effect of processing is of course of main interest in integrative computational material engineering. At the core of our know-how is the accurate material modeling to deliver the best results in CAE. And with the fast-growing market of additive manufacturing, Digimat is again bridging the gap between processing and final properties. The rise of artificial intelligence is a challenge and a chance for ICME. Finally, going back to the real world and closing the loop of Hexagon strategy, digital continuity will end the presentation. Let's start with the virtual material development, a topic that will be presented by Dr. Monsef Salmi, who is part of the engineering service team. The presentation will last 7 to 8 minutes.
Welcome to this short video introducing to you the virtual material development and connection to molecular dynamics. Let's remind that since its birth 15 years ago, Digimat was designed since the beginning to be a fast, robust, and easy tool for the user. Second, Extreme customers benefit from premium support and expertise, which is more than welcome, especially in such challenging environments. Third, Extreme and Digimat main mission is to bridge the scales and disciplines in a efficient and effective manner. Bridging scales and disciplines is key when dealing with virtual material development. Indeed, the goal is to connect the dots starting from the molecular scale until the structural scale. When dealing with virtual material development, there is a key notion which is virtual screening, standing for testing different configurations of microstructures and possibilities of combination of different materials. Digimat tools are built such as it makes it possible to test different configurations and types of materials, microstructures, and processes, which is key when developing virtually new materials. Once the designer defines the process and the microstructure that he wants to use in his next challenge, the idea and the next step is to refine the design of the new material by testing and, again, virtual screening different local configurations and architectures, like testing the effect of different volume fractions or filler amounts, the effect of fiber orientation, the effect of aspect ratio, or the effect of fiber type. Enough theory. Let's now move to concrete case studies in both the mesoscale and the molecular scale. First, let's begin with the mesoscale. The first case study stands for investigating the ideal trade-off between stiffness and density for a foam microstructure. Foam microstructures can come with different types, whether it's an open cell topology or a closed cell topology. It can also correspond to different amounts of voids inside them. The idea of this case study is to find the best trade-off between the relative density and the relative stiffness for such microstructures. And as we can see it, the Digimat tools can predict accurately the experimental data that is plotted here in blue dots by comparison to the red dots corresponding to the Digimat FE predictions. This is a first step and can be extended to more complex behaviors like the prediction of damping, failure, and damage using ad hoc meshing and solving technologies. The second case study for virtual material development from the mesoscale is investigating the ideal reinforcement type and amount. So the question here of the designer is whether to use carbon fibers or glass fibers, and then with which amount of volume fraction. With this activity, we can make the comparison between 25 combinations, setups, we run it and plot it in less than 2 hours. When we compare such activity with physical material development, the latter can take up to months in order to perform such study. The third case study for virtual material development from the mesoscale is focusing on the highly emerging material process nowadays, which is the 3D printing. The idea here is to use the multi-scale workflow for characterization of metal and polymer lattices for 3D printing. One of the major parameters optimize the architecture of the lattices that are printed to the structure. And the idea here is to virtual screen different configurations of architectures and end up with evaluating the thermal, warpage, and stiffness impact that this architecture has on the final structure. Let's dive now deeper into the scales and going onto the molecular scale. And let's connect the dots between the atoms of the material and the final structure performance. First case study is focusing on the usage of molecular dynamics for feeding Digimat with a microstructural configuration. In this framework, the considered application here is to optimize the positioning of silica particles inside rubber for tire applications. In this framework, Schrödinger software for molecular dynamics is used in order to make the link between the molecular energy surface of the silica particles and their impact on the final configuration of spatial distribution of these silica particles. The next step of the workflow is to use this result of molecular dynamics in order to feed DGMAT tools in general and DGMAT FE in particular with the positions of the particles, and then build an RVE and deduce the stress strain curves. The next case study stands for using molecular dynamics and DGMAT for material failure assessment. The idea here is to start from the atomistic chemical formula of a given resin. Then, by using molecular dynamics softwares in order to assess the limit strain invariant failure parameters of the resin and feed the DGMAT mesoscale model with the resin failure properties, and then DGMAT are able to compute the macroscopic composite failure. Hence, we make the direct link between the resin chemical formula and the final structural performance. The next case study is to optimize the graphene positioning inside a given resin in order to enhance or optimize the thermal properties of the resin, hence enhancing the global macroscopic thermal properties of the corresponding CFRP. The figures here compare the structural thermal behavior without any graphene particles, then the structural behavior with graphene particles corresponding to different distributions due to different molecular properties of the graphene particles. Hence, we make the direct link between the molecular properties of the graphene particles and the final structural part.
Thank you very much, Monsef. This was very impressive and must accelerate greatly material development. The screening topic was especially a source of great savings. I hope this will give ideas to our audience. Pierre Savoya will now talk about virtual testing. Pierre is product manager at Extreme Engineering. The presentation will last approximately 6 minutes.
We see an increased number of grades for a given performance. Indeed, different reinforced thermoplastics cover a similar range of applications, and other composite materials such as SMC and fiber mats bridge the gap from SFRP to CFRP. This has a direct impact on both material screening and characterization. Material characterization is expensive due to the number of options to evaluate. First, because multiple grade variations such as fiber content are considered. Second, because a wide range of environmental conditions including temperature, moisture, and aging should be covered. And finally, because design engineers now target advanced performances such as creep and fatigue, which tests last longer and therefore are more expensive. Once a micromechanical model is calibrated on a reduced set of data, the strength of our approach is to predict composite mechanical response in other configurations. Such work allows to combine a minimum of real tests with virtual tests to generate a wide range of data at composite level. DGMAT enables several approaches of virtual testing. One approach consists in using DGMAT as a virtual lab in order to compute composite mechanical response in other microstructural configurations. This allows, for example, to estimate material response at other fiber content. Another approach benefits from its own product to capture variability sources at coupon level. The end goal is enabling evaluation of stacking sequence and to complement real tests with virtual ones, reducing the cost of very large test campaign. One last example is the estimation of the effect of defect at coupon level, which leads to knockdown factors to be applied to design point. Here can be addressed effect of defect as well as of manufacturing. To consolidate those factors, DGMAT allows to evaluate effect of some defects in different configurations for many tests. Those are only examples, and we can think about many more approaches relying on DGMAT bricks. DGMAT requires a certain number of inputs in order to calibrate material cards. Such list of tests most likely becomes unaffordable when targeting calibration of many grades at multiple fiber content in numerous environmental conditions and for many performances. A different approach can be envisioned by relying on numerical simulations to predict composite response and use a mix of real and virtual test data. DGMAT-MF and DGMAT-FE can be used to calibrate a phase model, which can then be used to predict composite response of any microstructure. This typically allows to look at other fiber content without investing in extensive characterization campaign. Relying on those tools as well, a meta-model approach would allow to calibrate a global model which could be adjusted to fit a reduced set of tests. Such model can account for many dimensions, including environmental conditions, microstructure, aging, etc. The true strength of such approach is that the more dimensions are considered, the fewer tests are required. In other words, the cost of additional material cards drops with additional dimensions. In addition, based on this meta-model, interpolation of material cards for exotic conditions become possible instead of having to perform dedicated test campaigns. Those are the basement bricks of virtual testing wall, allowing to rely on combinatory matrix and virtual test data at best. Inspired from aerospace industry to compute allowables and design values, DGMAT VA relies on a building block approach to isolate variability sources. Different levels are introduced to cover, first, constituent variability from batch to batch, meaning matrix or fiber quality, for instance. Second, process variability from panel to panel, where first layer is fiber content. And post-processing variability from coupon to coupon, targeting alignment accuracy with respect to loading direction. Simulating contribution of those variability sources at coupon level provides a cloud of response, allowing to compute virtual allowables and design values. Once each variability source is identified and quantified to capture average values as well as allowables such as A basis and B basis, the model benefits from a greater trust. It means that for many stacking sequences and in many mechanical configurations, the variability is captured. From this point, the strength of this approach is that new stacking sequences and test configurations are now virtually accessible with few simulations. In other words, allowables for other stacking sequences and additional tests can virtually be computed to lighten real test campaign. This is a serious plus when looking at the 1,000 coupons test required for material certification. Parts are unfortunately manufactured with defects, even though we try not to. Therefore, design part must fulfill intended function with presence of defects. To design part in such circumstances, margins are used to knock down pristine material allowable into design values. The trade consists in tolerating number of defects in a part, which effect can be covered thanks to knockdown factors as a safety margin. It appears that such margins are challenging to evaluate and to separate from previously presented variability aspects, material, process, and post-process variabilities. DGMAT VA allows to simulate different defects at coupon level, including porosity, intra-ply and interply, ply waviness, as well as ply debonding. Resulting coupon simulation provide defects associated knockdown factors. Our target is to equip material engineers and design engineers so that they can virtually compute defect knockdown factors efficiently and accurately. With this tool, your team can consolidate knockdown factors for certain defects, trade between design margin and defined tolerances with greater confidence, and face non-conformity requirements with more powerful tool than engineering judgment.
Switching back to the slide, your presentation is showing huge potential savings regarding material characterization. We know that the labs are heavily loaded because of demands coming from customers. And generally, customer demands are very often different from one to another. And the use of meta-modeling can greatly reduce the number of real testing required to answer such demands. Let's now switch to our third topic, which is material lifecycle management. Material Center is a software solution to manage material data information across the organization, and it is the backbone of the 10x ICME solution. It will be presented by Najib Beg, who is the product manager of Material Center. This will last approximately 6 minutes.
So what are some of the challenges related to materials information management? If you look at a typical product development process, you have hundreds of parts with material specifications. You want to avoid multiple sources and inconsistent usage of materials data. Design engineers need access to their design properties. Materials and process groups lack traceability of their materials data. Manufacturing lacked understanding of material, process, and part performance. Compliance department wants to avoid restricted substances and conflict materials in design, while CA wants to ensure efficient and correct CA models. What is the cost of all these challenges? You may face costly product failures due to incorrect usage of material properties. A typical engineer can spend up to 1.8 hours per day just looking for data. Data loss is a very common problem, and on average, organizations lose $4 million worth of data every year. Manufacturing can face increased research and development time and hence increased time to market due to gap in understanding of the process. If you're not compliant with your products, you can face fines and imprisonments, while the consequence of using incorrect data in simulation may lead to incorrect design. What Material Center allows you to do is to introduce material strategy into your organization. It allows you to capture all of your materials data in a single location. And using the web applications, your end users are able to access, search, compare, and export this data. Design engineers can access the design specification not only through the web application, but also directly within their environment in CAD and PLM. MMP groups can manage all of their data, including tests, virtual, and analysis data. Manufacturing can capture the entire process from material to process parameters to final manufactured parts. Compliance can manage materials with CAS and composition number in a single location and then be able to run compliance checks instantly on the latest legislation. CA can access and generate CA models quickly from the web application or from within their CA applications such as Abacus and ANSYS. Material Center is an enterprise application that meets the stringent requirements for enterprise deployments in different industries, including aerospace. The application is prepared with access control and full version control capabilities. Let's look at a software demonstration of how you can consolidate and centralize all of your materials data. You will see how you can import your data from Excel to create a single source for your entire organization, and using our application for accessing the data, searching, and comparing. And finally, we'll show our integration to access that same data through CAD and CA. So you can see we have a material specification in Excel. Within Excel, you can publish the data directly to Material Center. You can automate this process as well if you have multiple sheets. You have all your global spec in single location here, as you can see. On the left-hand side, you have all your materials organized according to your material characteristics. You have all the access control, the version control needed, as well as the property overview. Here's a typical data sheet where you're capturing all the key information, such as composition, electrical properties, hardness, mechanical. You can do quick searches in a similar fashion as Google to find any material across all of your materials. You can filter those against properties. And here you can see a comparison of some implicit materials knowledge, where can it be used, previous experience, previous failures with this material, any recommendation from the materials expert that needs to be communicated to design. Now, the same information can be accessed through CAD, as I mentioned. There's no point of having a single source if you can access it through your environment for designers. We have an integrated app plugin that allows you to access the same data where you can choose the material model or the properties that is needed for your design. That could be material specification, material name, supplier name, And all that information is then persisted into the model itself. As you can see here, you have the material itself along with the key properties. In a similar way, you can support advanced simulation models. Here's the same data, the same database that we were accessing. The CA engineer can search and find relevant data and import any type of material model. So in this case here, we're importing a Nastran model, but in a similar fashion, you can create your own simulation models, whether that's for Abacus, any type of cards that you need for ANSYS or any other solver. That model is generated automatically, so you save time in terms of creating those simulation models, and those are directly available within the CA solver. The key benefit here is, of course, you have a single source, you have accurate information, you have the model generation done automatically, so you're reducing all those three risk points that I was talking about before.
Thank you very much, Najib. This is a dream made real. Having organized information all over the organization and stopping losing time searching for data. I think everybody in there is looking for this. After a long career in simulation, I find personally the CA export very exciting, as I remember very often each engineers wanted to generate the material cards using their own tricks, sometimes leading to discrepancies at final users. With Material Center, anyone who is authorized can generate material cards, and every time it will be the same card that will be generated. This brings confidence at customer level. Developing technology is not the purpose. Sharing technology is what we target, as far as we can protect our IP. Let's now talk about Digimat MX and see how to leverage your ICME technology. Since 2011, material exchange is experiencing growth. This is due to a strong demand of end users to design and optimize their parts. A strong demand for end users to better understand the materials they use and push the limits. Material suppliers' contribution is huge. There is a significant investment from their side to promote their materials with Digimat models. As we will see, it seems the market is asking for more. Listening to you, this is what we hear. Many are claiming for more materials, more data, and more models. Lots of you want accuracy, reliability, confidence, and transparency. Some want material usage dashboard, an on-demand database update, and reduced administration tasks. They also want to reduce characterization costs, protect their IP, and gain in visibility. Others are asking for methodology and alignment with standards. A few want to reuse existing measurements and make anisotropic from isotropic. Some key players are requesting material model evaluation, as well as material comparison and selection. And all of you are concerned by IT security. Whatever the need, material exchange is a link. Material exchange is the place to find the best of ICME, and the story is not ending tomorrow. Here is our vision. Tomorrow we'll see an increase of new materials. In automotive and aeronautics, reduction of emissions, sustainability and electrification will continue. The automotive trend of autonomous driving will put even more constraints on design. Whatever the main field of application, the future is multiphysics. Tomorrow will require more material engineering and more material models than ever. We must be prepared. With Digimat MX, all your investment in ICME is rewarded with increased customer intimacy. The customer request is passing through Digimat MX, so it can be answered with encrypted file to protect your intellectual property. Digimat MX is the pipe you use to push your ICME skill to the desk of your partners. Let's now talk about compliance and sustainability. Najib will present this part. Najib is our Material Center product manager. We will see what can happen in some companies having compliance management issue, and then how Material Center can solve this.
If you look at the final aspect here in terms of compliance and sustainability, there's a lot of challenges related to material compliance. There's no control on what materials are being used in products. Materials information is disorganized and spread across different departments on local computers, file cabinets. So the compliance departments are really having a difficult time to control the process and ensuring that no one's just using restricted substances. There's typically no access to latest legislative information, and new legislations and substances are generated every day. So it's a very challenging and a complex landscape. So what you can do with Material Center is to, as you have seen, create a single source of your materials and compliance data that is securely managed with complete traceability and access version control. Through our partnership with iPoint, who are market leaders in the compliance sphere, you can run instant checks on compliance and always get the latest information on REACH, RoHS, SVHS, just to give you a few examples. But they have a full comprehensive suite of legislations, and they also have specific product solutions for running part compliance checks. Using our integration and collaboration, you can run scheduled runs on all your materials every 10 minutes, every 24 hours to set up the system. And then you're able to get the latest compliance information for your whole organization. So let's look at a demo on that. So here we're importing some compliance data. As you can see, it's different materials, and we're publishing the data into Material Center. In a similar fashion, you have the same single source with key composition data and cast information within the system. And everyone is using this. And then you can run compliance check either interactively, and this information is sent to iPoint, which gives you instant information whether your materials are compliant or not. And here we can see we are evaluating 4 different suppliers, and 1 supplier is non-compliant. You can also get an overview of all of your materials to get a summary report. And here we can see there's 1 material that is non-compliant, and it's the same supplier B that we're looking at before. Now, in a similar, for other use cases, it's critical that we have the same access for the designers as well. So they are aware of the compliance information, so they're not assigning or using material data that is non-compliant. So here you can see the design engineer, first the compliance department did their checks, managed all the data, and now they're communicating that information to the design department so they can understand which materials they can use and which they can't, or which they should avoid.
Thank you, Najib. It is very interesting to see how Material Center can push compliance information right to the hands of designers, avoiding further troubles. The point number 6 of our 10x ICME solution is the effect of processing. It will be presented by Florian Metzger, who is application engineer, part of the customer services team. The presentation will last about 7 minutes.
All over the industry, different materials and with them different types of manufacturing processes are used which will have direct influence on the final part performance. To precisely predict your part behavior, it is therefore necessary to know the effects of manufacturing by taking into account process data and simulations. Therefore, Digimat offers various ways to predict the effects of manufacturing on the final part for different applications. Some examples are automatic tape or fiber placement, thermoforming and draping of continuous fibers, 3D printing of filament or powder-based plastics, injection molding of short or long fiber reinforced plastics, and the curing of thermoset matrix composites. Let us begin with automatic fiber or automatic tape placement, which is a very efficient method to produce large parts made out of continuous fiber composites, for example in the aerospace industry. In this method, a robot head places tapes of fiber rows automatically in a predefined way on a surface. The robotic control software drives the system and is very important as it forms the design and the manufacturing interface, bridging the gap between the as-designed and the as-manufactured part. The strip deposition process generates composite structures containing very specific microstructures, like it is illustrated here. In such a case, Digimat will be able to determine the defects and their influence on the part and its performance, define how many defects can be tolerated by a certain design, and optimize the manufacturing process without producing a single prototype. The second topic is the thermoforming and draping, which is another method to produce continuous fiber composites, especially for higher part quantities. During the forming of the part, the material is locally moved and pulled in different directions. This influences the fiber direction, but it can also cause wrinkling in the corners. Coupling Digimat with a thermoforming or draping tool allows you to predict various effects on the material and part quality. It allows you to determine the thermomechanical response of the material and the local influence of the manufacturing process on the microstructure. This information is then used to simulate residual stresses, warpage, and part performance. With additive manufacturing or 3D printing, the design engineer has a lot of freedom for innovative designs and optimal load distributions. However, this manufacturing method also comes with its limitations and difficulties. With additive manufacturing or 3D printing, the design engineer has a lot of freedom for innovative designs and optimal load distributions. However, this manufacturing method also comes with its limitations and difficulties. Additive manufacturing will allow you to design a great part, but its performance directly depends on the printing process as it is driven by the toolpath and print direction. Digimat helps to evaluate the influence of the printing toolpath in multiple steps. First of all, the Digimat material card will help to describe the complex anisotropic material behavior that depends on the local filament direction. Additionally, Digimat helps to detect toolpath gaps in your part. Those gaps are voids that appear between filaments and create weak spots in the printed part, which can cause early failure. Being aware of this allows the engineer to optimize the printing strategy for a better part performance. Originally, Digimat was made to bridge the gap between manufacturing and structural performance by taking into account the local fiber orientation of fiber-reinforced parts. This is what allows us to do precise simulations of short and long fiber-reinforced plastic parts. To obtain the overall fiber orientation of the part, one can either scan already manufactured parts with CT scan technology or run injection simulations to test and optimize the manufacturing method virtually. Nowadays, Digimat RP contains the integrated fiber estimator to quickly obtain a realistic estimation of the fiber orientation, which leads to a more precise simulation. In its latest release, Digimat can use solid as well as shell meshes to run the injection simulation, and it can also predict weld lines and their effect on the structural performance. Next to the direct simulation in RP, it is also possible to take into account a large variety of manufacturing effects, such as porosities, residual stresses, warpage, variable fiber content, and many more. Last but not least, I will introduce you to the curing of composites, which is a critical point for the manufacturing of thermostatic composites. Curing usually describes the hardening of a resin using elevated temperatures to obtain the final material properties. The problem of this process is that often parts deform and end up with residual stresses that can make the part unusable. Especially internal stresses in corners or roots can influence the structural performance and create delamination of layers within the material. Digimat helps to predict such critical areas in order to avoid creating weak spots in the manufactured part.
Thank you, Florian. It is very impressive to see how Digimat has brought diversity in its portfolio. We are far from software dedicated to injection molding short-glass fiber materials. Now Florian will present the seventh topic about accurate material modeling. The presentation will last about 4 minutes.
First of all, we should ask ourselves, why do we actually need accurate material modeling? Taking composite materials as an example, the physical properties highly depend on the single components in the material, but also on the local microstructure. This will lead to complex nonlinear anisotropic behaviors, which are, in addition to that, depending on temperature and strain rate. Also, failure and damaging can be highly complex. Furthermore, all those properties can change locally all over the part and depend on things like fiber distribution, volume fraction of the fibers, porosities, weld lines, initial stresses, and many more. To be able to consider all those details and to create a true digital twin of a material, the industry needs accurate material modeling. The 10x ICME solution brings you the tools to cover all parts of accurate material modeling. Our material models bring you the nonlinear behaviors for static, crash, fatigue, and creep, which are able to give you a fully anisotropic stiffness damping on failure. Like this, our failure mechanisms allow you to model realistic failure envelopes with progressive damaging and include static, dynamic, and also cyclic fatigue failure models. Finally, all those parameters can be made strain rate and temperature dependent to fit exactly your loading scenario, covering everything from static creep to crash and vibrations. In order to define such complex material models, we created a reverse engineering process that allows you to turn your experimental data into material models, taking into account the constituents and microstructure. With the newest version of Digimat, you will be able to reverse engineer thermal expansion, static and dynamic stiffness and failure, temperature dependencies, strain rate dependencies, cyclic fatigue failure, frequency dependencies, and creep and stress relaxation. Once you created your advanced material model, we offer you Digimat RP, which is an incredibly easy to use interface to apply the material in your analysis, even for large assemblies. In just a few clicks, Digimat RP can generate a working material model directly from your experimental data curves. Then load the microstructure information on your part and you're ready to submit your analysis using our accurate material models. All this is done directly through one single interface. Since our latest releases, Digimat RP can also post-process fatigue analysis and give you life cycle predictions on your parts. If all this is not enough, we also offer you full field homogenization, which is capable of modeling every complex material. You can create any possible microstructure and analyze it to determine the physical properties of the material. We are permanently improving our models and algorithms, so our recent developments allow you to create more realistic RVEs, improve the mesh, apply new failure models, and solve your simulations up to 100 times faster to get the true experience of accurate material modeling.
Thanks again, Florian, for this presentation. I didn't realize how many behaviors we can now reverse engineer in Digimat MX. This is huge. We can address many behavior types, and we're not finished. Now it's time to talk about additive manufacturing. This fast-growing technology will be presented by Dr. Olivier Moulinjeune, Business Development Manager in charge of additive. The presentation will last approximately 6 minutes.
This slide was presented by Oren Zoran from Stratasys at our Digimat users meeting in 2016. Though a lot of companies were already using 3D printing for prototyping, he estimated that we still had 3 to 5 years to start direct manufacturing. 3 years later, we do see additive manufacturing being more and more used for production. Our ambition at Xtreme is to support this market move with numerical simulation. We want to increase the number of high-performance materials, to ensure more accurate and reliable parts, and be able to predict the part performance. In summary, in terms of the needs, we want to propose the same validated engineering workflow as more traditional manufacturing techniques as injection molding. In terms of the challenges, the process reliability and its complexity, a lot of parts still suffer from warpage, from shrinkage, from part elimination from the printing bed. 3D printing parts will often show anisotropic behavior, even for non-reinforced materials, because of the toolpath or the build orientation. There is a lack of knowledge and a lot of trial and error techniques. The solution that we want to propose to the market is to propose to predict warpage and compensate for warpage, to derive accurate material models ready to use, and to predict the as-printed part performance. And of course, you can always rely on our expertise, and we are able to develop any methodology for your own use. The solution that we propose with Hexagon MSC software on additive manufacturing is made on topology optimization with Amendate and MSC Apex. The different DigiMat tools and solutions that constitute our additive manufacturing solution create three main building blocks: material engineering, process simulation, and part performance for FDM and SLS processes. And finally, you can inspect the part with Hexagon scanners. We haven't built this solution alone. We have created a full ecosystem of material suppliers, printer OEMs, R&D centers, and end users. Today we will illustrate two of these partnerships, the first one with Stratasys. If we consider the usual printing workflow, we start with the design, some pre-processing to slice the part, to define the tool path, we print physically the part, and then we do some post-processing. Our ambition with Stratasys is to integrate numerical simulation at the heart of this workflow, to first define what is the best material for the usage, to optimize the process and minimize warpage, and finally to master the performance of the part. With Stratasys, we've been working at developing material models of the Ultem 985, 1010, and the 912CF for process simulation and structural analysis. We also have a full package for the printer model of the Fortus 900 MC, and thanks to our partnership, we have a direct access to inside toolpath data. DigiMat AM aims at printing right the first time, predicting warpage and residual stresses. In DigiMat AM, you will select the manufacturing process, the printer. You can define the part, which is a STL file format. You need to select the material from our database, in this case the Ultem 985, and then you can input the toolpath and define a couple of process parameters. Finally, we need to mesh the part before we can submit the job. Then you can analyze the warpage analysis, so what are the deflections that we see, create an animation of the full build, review the residual stresses, and export some simulation results. And finally, we can compare with scanning data. The second partnership that we want to highlight today is with Solvay. Solvay is developing materials for FFF with PEEK reinforced with carbon fibers, and PPSU, and in SLS with PEG powders. These are a couple of examples where we have been able to help Solvay by modeling the as-printed material microstructures, working on fibrous reinforced materials, and defining a multi-scale workflow for lattices. And in terms of part performance, we want to optimize the printing strategy to simulate reinforced filaments and test partial infill for lightweight parts. The objective is to predict the fiber reinforced FFF part performance with the same ease of use as for injection molding, and for this we use DigiMat RP, which is now open to fiber reinforced FFF as the Ketaspire P carbon fiber filament from Solvay. So by taking the toolpath into account, the engineers are now able to predict what will be the maximum force that the part can sustain and compare that between different building orientations or comparing that with injection molding grade.
Thank you, Olivier. Before to close this topic, we can mention the partnership we have with DSM in the field, with 4 materials available in DigiMat already, and maybe more to come. Our topic number 9 is about artificial intelligence and how we can apply it to materials. This presentation will be given by Philippe Ebert, Product Manager at Extreme Engineering. The presentation will last about 4 minutes.
Material intelligence means artificial intelligence applied to materials. And today we'll have a look at two use cases, one for virtual variables, the other one for smart multi-scale modeling. Let's start with AI for virtual variables. AI for virtual variables means training an AI model with hundreds of thousands of experimental data and simulation data points, which can be worth millions of euros and decades of labor. The idea is to be able to predict in a fast and accurate fashion virtual variables for other combinations of material systems, stacking sequences, coupon geometries, and environmental conditions than the data that were used for the training. Let's have a look at a very concrete example. In the next example, the training data that was used consisted on one side of 15,000 simulation points and 56 experimental data points. The first step consisted in training the model with Digimat VA predictions. As you can see here on the graph, the machine learning, represented in green dots, is able to capture quite well the predictions of Digimat VA, here in orange. However, at this stage, the experimental data points have not been used yet to train the machine learning model. So a second machine learning model is created, which is based on additional training with the experimental data, which are here represented in blue dots. As you can see here on the graph, with the purple dots, the response of the second machine learning model is closer to experimental data, therefore more accurate. This demonstrates the need to work both with simulation data and experimental data to have accurate AI predictions. First conclusion from this exercise is that the AI can bring the VA predictions closer to experimental data. One should note that AI cannot compensate for the fact that physics that would not be included in the simulation cannot be captured. As next steps, we would like to extend to other material systems than UD materials. We would like to improve the physics in the Digimat VA material model to be able to capture them with the AI model, as well as include more experimental data values to train the machine learning model. Let's now have a look at AI for smart material model. The idea with AI, a smart material model, is to train a model with tens of thousands of simulation data coming from microscale simulation under different loading conditions. What we can then achieve is a fast and accurate prediction of the material behavior at the macroscopic scale by artificial intelligence. In the next example, the training data that was used consisted of 7,500 macro stress strain histories with 100 points, each predicted by Digimat FE with a single FE model, which was actually worth 80 days of CPU time. The modeling strategy consisted of predicting the stress based on the applied strain, as well as a series of internal variable evolution, namely strains, stresses, and plastic strain, both macroscopic and in the fiber and inside the matrix. When training the machine learning model on the Digimat FE predictions, one can check what is the correspondence of the model response for some specific load histories. As you can see here, on 4 random load cases, the machine learning model in red corresponds quite well to the data that was used for training, which is here in green. Conclusion from this exercise is that the first machine learning model was developed to simulate the elastoplastic behavior of a UD material. Machine learning offers great potentials to develop and deploy high-fidelity material multi-scale models with barely no computational requirement for the end users, as these have been all applied upfront. As next step, we intend to improve the accuracy of machine learning models using more simulation data, as well as extend the models to variable phase properties and microstructures, and enhance as well to damage and failure predictions.
Thank you, Philippe. It is always surprising to see how artificial intelligence can provide fast computation with somehow good accuracy. Nevertheless, as you mentioned, the physics we want to capture must be in the simulation used to train the artificial intelligence. It means we can still continue to improve Digimat with more and more complex physics inside. Philippe will now hand his presentation with the last topic of our 10X ICME, digital continuity.
Hi, my name is Philippe Habert, Product Manager at Extreme. Welcome to number 10, Digital Continuity. Digital continuity is the application of the 9 previous building blocks in a framework that allows to solve custom and specific engineering challenges. It supports the development of the next generation of manufacturing and Industry 4.0. One example of digital continuity is additive manufacturing. At Hexagon, we provide a solution specific to additive manufacturing. It combines Hexagon production software, design and engineering software, and metrology scanners. It enables to plan, optimize, validate, and replicate high-quality additively manufactured parts. This solution is the combination of part geometry, topology optimization, smart AM machine and material selection, process optimization by simulation, first-time right production, metrology for quality assurance, and metrology for reverse engineering. All these steps being backed up by a robust and efficient data management system for the entire process. Let's focus on the machine material selection as well as the process optimization by simulation. In the next example, we could ask ourselves, for the following bracket, which orientation should we choose to achieve best process and part performance, knowing that the material has been fixed, being a polyamide reinforced with carbon fibers. We'd like to choose between 2 orientation possibilities, one where the bracket is oriented, one where the bracket is flat. What we want to achieve is a smart decision combining different factors such as print time, part weight, dimensional tolerances, stiffness, and strength. To define the dimensional tolerances, we first run a process simulation of the part for the 2 different printing conditions. The conclusions from the process simulations is that excessive warpage is occurred by default and warpage compensation is required. Through warpage compensation, we are able to validate both printing strategies to meet the dimensional tolerances. We can then move on with structural analysis to assess both the stiffness and strength performance of the part. This is done by running a coupled finite element analysis accounting for the local manufacturing history, the local microstructure of the material. The simulation predictions provide very strong indication of which is the best orientation to choose. Indeed, when we choose the oriented approach, we obtain a stiffness which is twice smaller than for the flat, while the strength is approximately 1/4 of the strength for the flat orientation. Therefore, through this simulation chain, we're able to choose the flat orientation as the best orientation that combines process quality, part performance, as well as optimal print time.
Thanks, Philippe. We like to see simulation as part of the real world. This is where it brings the more value. The presentation is now ending. We hope you enjoyed this journey through all the capabilities offered by Digimat and Material Center. We expect this will give you many ideas for early tomorrow. Thanks for your attention.